Bismillahirrahmanirrahim. Assalamualaikum and a very good day. First of all, I would like to thank all of you for having me on my session. Okay, today I will share with you all my study on nanoparticles in soft microagglomerates as oral colon-specific cancer therapeutic vehicles. Okay, according to Global Cancer Statistic 2018, colon cancer is the third highest cancer incident mortality worldwide. Development of colon cancer is encouraged by a few risk factors, which are diet, smoking, obesity, alcohol drinking habit, family history, age, pH inactivity, and as well as inflammatory bowel disease. Okay, conventional and existing approaches used in colon-specific delivery are prodrug, pH-dependent system, time-release system, microflora activated system, bioadhesive system, and multi-particulate system. Okay, most of these systems, they are actually adopting tablets, pellets, and even microparticles as a colon drug delivery system. However, in the case of my study, we are actually designing nanoparticles as cancer therapeutic carrier specifically to the colon. Okay, nanoparticles with small size, large specific surface area, perhaps can interact with the receptor of the colon cancer and to a greater extent can be decorated or conjugated with targeting ligand. Okay, the targeting ligand carried by nanoparticle can interact with cancer cell folate receptor. However, there is challenges of delivering nanoparticles orally because of being small. It's prone to interact with gastric fluid, intestinal fluid, and thus contributed to premature drug release. And to enable us to carry cancer therapeutic to the colon in a targeting manner using nanoparticles, we actually further design or transform the nanoparticle into nano in microparticulate system. Okay, basically there are three types of polymer used in this study. Okay, first is a chitosan, which are used for nanoconjugation and as a microcarrier, pectin for complexation, and alginate for intracapsular coat. Okay, this study firstly comes with the design of nanoparticles and nanoparticles aggregation vehicles. Okay, the nanoparticles are prepared from chitosan folate 5-FU conjugate in co-observation with pectin, whereas nanoparticle aggregation vehicles is prepared from chitosan of different polymer solution concentration. Okay, both particles are produced by nanospray drying method. Okay, blending of nanoparticles and aggregation vehicles occur in vortex. The nanoparticles and aggregation vehicles are mixed in a specific ratios ranging from 1 to 18 up to 18 to 18. We also have a different variants of aggregation vehicles prepared from different solution concentration of chitosan. Okay, open mixings of nanoparticles and nanoparticles aggregation vehicles. The nanoparticle deposited on the surface of aggregation vehicle, which is in microscale, and once we blend them, due to plastic deformability and softness of the particles, these particles tend to cluster together, forming a bigger size particle which is known as soft agglomerates. And in our experiment, we actually have additional steps whereby we coat the soft agglomerates through intracapsular coating material, which is sodium alginate. The nanoparticle, the soft agglomerates, and intracapsular coated soft agglomerates are then subjected to the physicochemical study and drug dissolution study. Okay, now let's take a look what is my findings. In this study, you can see that folate and CMFU has been successfully conjugated to chitosan. Conjugates are characterized by FTIR and NMR. The presence of folate in chitosan was detected at 1704 FTIR peak and at 7.2 and 7.7 ppm of NMR peak. Coupling of CMFU to chitosan folate conjugate was confirmed by the NMR signal at 4.3 and 7.7 ppm. A nanoparticle produced by co-observation of chitosan folate 5FU and pectin was confirmed by FTIR analysis, where there is reduced in wave number at 1615 peak, which attributed to CONH interaction. The formed nanoparticles is semi-crystalline in structure, unlike CMFU, which is highly crystalline. Generally, nanoparticles is spherical in shape. Okay, what about nanoparticle aggregation vehicles? Okay, this slide shows aggregation vehicle prepared via nanospray drying of chitosan at different solution concentration. And here you can see that the size span generally larger when more concentrated chitosan solution concentration was used to prepare the aggregation vehicle. Okay, surface texture of particles get rougher when higher chitosan solution concentration used, and likewise for the crystallinity. Having prepared nanoparticles and aggregation vehicles, we then subjected the blending of them from the investigation of the possibility of them forming soft agglomerates. Okay, you can see here that the soft agglomerate begins to form after 3 minutes of vortex and get rounder with time. In soft agglomeration, you can see that ratio of nanoparticles to aggregation vehicles play a role, where increased ratio of nanoparticles to aggregation vehicles from 1:18 to ratio 10 to 18, the size, span, roughness and crystallinity increase. Okay, referring to SEM image, the formation of agglomerates prepared from ratio 1 to 18 to 10 to 18 involves deposition of nanoparticles onto aggregation vehicles and binding of particles under the influence of vortex forces into large agglomerates. Okay, the particles were bound basically via weaker physical adhesion. Nanoparticles and aggregation vehicles' individual characteristics remain visible on the surface of the agglomerates. Unexpectedly, after a further increase in nanoparticles to aggregation vehicles to ratio 18 to 18 gave rise to the formation of smaller agglomerates. The excess nanoparticle could have preferably bound to each other in addition to deposit onto the aggregation vehicles. Okay, the formation of nanoparticles on aggregation vehicles was reduced, and thus disfavoring the formation of agglomerates. Okay, in this slide, I would like to highlight the physicochemical effects of aggregation vehicle on the formation of agglomerates. Okay, in this study, the weight ratio of nanoparticles to aggregation vehicle used is kept at 10 to 18 ratio. Generally, when aggregation vehicles is larger in size, higher span, rounder and rougher, it will translate to soft agglomerate that is larger, low span, rougher and higher in crystallinity. Okay, larger aggregation vehicles provide a platform of agglomeration. Rougher surface texture of aggregation vehicle could promote nanoparticle deposition, and its roundness of aggregation vehicle allow the assembly of nanoparticles to aggregation vehicle into agglomerate through interspersing the smaller size fraction between the larger counterparts. Cross-sectional study of agglomerates shows that nanoparticles were deposited onto the aggregation vehicle, and small nanoparticle on aggregation vehicle were randomly located between the larger nanoparticle on aggregation vehicles. The particulate system are weakly bound with minimal signs of coalescence. Okay, soft agglomerates prepared from aggregation vehicles made of 1% chitosan solution concentration and at weight ratio 10 to 18 nanoparticles to aggregation vehicles is desirable as it possesses larger size, low span, rougher and higher in crystallinity. Okay, we then prepare drug-loaded nanoparticles where CMFU is covalently conjugated to chitosan. The nanoparticles is then subjected to soft agglomerates or intracapsular coated soft agglomerates. Okay, here I wish to show you the drug release data. The drug release study is conducted using transitional design, whereby we conducted drug release study for the first 2 hours in the simulated gastric phase, followed by the subsequent hours in simulated intestinal. Okay, you can see that the pure drugs are released relatively fast in gastric fluid. Same goes to nanoparticles. But however, formulating nanoparticles into soft agglomerate reduce the specific surface area, and as a result, you can see a lower drug release propensity is taking place. Okay, now how about with intracapsular coated nanoparticle? Okay, indeed, we do negate the drug release to show extent, but note that once the soft agglomerate is being intracapsular coated with sodium alginate, the lower drug release is active. It appears to us that soft agglomerate is more responsive to intracapsular coating than nanoparticle. So, the main finding is soft agglomerate is a must because they are more responsive to intracapsular coating by sodium alginate for whatever material that you use for nanoparticles. And this can further decrease the drug release through soft agglomerates and intracapsular coating. For the conclusion, nanoparticles alone are not able to agglomerate into large spherical entities. The introduction of aggregation vehicles less than 2 micrometer promoted soft agglomeration with nanoparticles deposited onto its surfaces with minimal signs of binary coalescence. Larger, rounder and rougher aggregation vehicles with wider particle size distribution promoted soft agglomeration. The large and rough surface aggregation vehicle provided an anchor to nanoparticles deposition and agglomerations. Its roundness allows assembly of nanoparticles on aggregation vehicle into agglomerates through interspersing the smaller size fraction between those larger populations. Soft agglomeration of nanoparticles reduced their propensity of early drug release and acted synergistically with intracapsular coating by sodium alginate to further negate drug release. The polysaccharidic nano-in-micro soft agglomerates can serve as a primary oral colon drug delivery vehicle. Lastly, I would like to thank Professor Dr. Wong Ting Hui, Non-Destructive Biomedical and Pharmaceutical Research Center, I Promise, Faculty Pharmacy, UiTM, Ministry of Science, Technology and Innovation, Malaysia, Ministry of Higher Education, Malaysia, for their support and funding.